Hello students, good morning. So today we'll discuss a few numericals from the section Young's double slit experiment. Hope you understood the theory part and you are able to derive the equation up to the expression for fringe width. Okay, so we'll move to the numericals. Our first question is: two coherent sources are placed 0.2 centimeter apart and the fringes are observed on a screen 2 meter away. The bandwidth produced by certain monochromatic source of light is found to be 0.6 millimeters. Find the wavelength of light. This is a direct question. As you know, two coherent sources are needed to produce interference. And we will get bands on the screen which will be bright and dark bands. Bands are also called as fringes. Okay, so here two coherent sources are placed 0.2 centimeter apart. That means you have a single source, then with the help of two slits you are making coherent sources, isn't it? This is a monochromatic source. Now, if there is a screen here, it will produce the interference pattern on the screen. It can be bright, dark, etc. So, here it is said that these two coherent sources, suppose if it is S1 and S2, these are separated or placed 0.2 centimeter apart. Okay, 0.2 centimeter apart. That means our small d, which is a distance between two slits, is equal to what? 0.2 centimeter. You can convert it into meters. That is 0.2 into 10 raised to minus 2 meters. Clear? Now, it is given that the screen is at a distance of 2 meter from the slits. Okay, so this is 2 meter, which we call it as D. Capital D equal to 2 meters. Now the bandwidth produced by certain monochromatic source of light is found to be 0.6 millimeter. So what is this bandwidth? It is the fringe width, isn't it? And we define fringe width as the distance between two consecutive bright fringes or bright bands or two consecutive dark bands, isn't it? So beta, it is represented by beta and it is given as 0.6 millimeters. You have to convert it into meter, that is 0.6 into 10 raised to minus 3 meters. Clear? So now you have the expression beta is equal to, what is the expression? Is beta equal to d lambda by d. D lambda by d, isn't it? So now you want to find lambda, that is lambda equal to beta into d by d. Clear? So you can substitute, that is beta as 0.6 into 10 power minus 3 into small d is 0.2 into 10 power minus 2 divided by 2. Okay, so what is the answer? As this will get cancelled. So finally the answer is 6 into 10 power minus 7 meters. Clear? 6 into 10 power minus 7 meters, or you can write it as 600 nanometers. Since it is wavelength, this wavelength will be of the order of nanometer or angstrom. So it is 600 nanometer or 6 into 10 power minus 7 meters. Okay. So this is a direct question. Here small d, capital D and then beta are given. You are supposed to calculate the wavelength of light. So by direct substitution you can calculate it. Clear? So we'll move to the second question. Now the second question. In YDSC, what is YDSC? Young's double slit experiment. The slits are separated by 0.28 millimeter and the screen is placed 1.4 meter away. The distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. Determine the wavelength of light used in the experiment. Okay, so first of all, 0.28 millimeter is the distance between the slits. So you can write here, you can write the given data, that is small d equal to 0.28 millimeters, or if you are converting it into meter, you will get 0.28 into 10 power minus 3 meters, isn't it? Then the screen is placed 1.4 meter away. So what is capital D? It is 1.4 meters. Okay. The distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. That means if you have a screen here there are two sources, okay, and somewhere here you are getting the band. Suppose this is the fourth bright fringe, then this is the central bright fringe. As you know, this center will be a bright band, isn't it? So from this distance, that means from 0 to 4th, that is the central bright fringe to 4th bright fringe is measured to be what? 1.2 centimeter, isn't it? So what is given there? What is given? Because this is the fourth one, okay. In between, how many are there? As this is starting from central bright fringe, then first, second, third, isn't it? After that fourth is coming. In between, dark bands are also there. And fringe width or band width is the distance between two consecutive bright bands or two consecutive dark bands. Here it is bright fringe. So how will you find beta? As beta is equal to 1.2, which is given here, divided by 4, isn't it? Since each band is of equal width, you can do it like this. So beta equal to 1.2 by 4, and it will be in centimeters, that is 0.3 centimeters. Clear? That is 0.3 into 10 power minus 2 meters. And what is lambda? Lambda you have to find, isn't it? Lambda, you have the expression from the previous equation you got. Lambda is equal to beta into d by d. Beta into d by d. Now you have beta, then capital D and small d. So you can directly substitute, that is beta equal to 0.3 into 10 power minus 2 into small d is 0.28 into 10 power minus 3 divided by 1.4. Okay, understood? How can we take this relation? Only because each band or the fringe is of equal width. Otherwise we can't take that. Okay, so beta equal to 1.2 by 4. If it is 6th, means 1.2 by 6, isn't it? Okay. Now after substitution, you have to find the answer. Okay. Find the answer and write the unit also. It's very important. Clear? So we'll move to the next question. So our third question. Two slits are kept 1 millimeter apart and the screen is placed 1 meter away. What is the fringe separation when blue-green light of wavelength 500 nanometer is used? So here the slit separation is given, that is small d is given. Then the distance of screen from the slits is also given, which is 1 meter. First you have to find the fringe separation. What do you mean by fringe separation? S is nothing but beta. Okay, So you can directly find it because small d, capital D and lambda or the wavelength is given, because here which color is used? Bluish green color is used, which has a wavelength of 500 nanometers. So first we can directly move to the expression, that is beta is equal to d lambda by d. Okay, that is 1 into lambda is 500 nanometers, lambda 500 nanometers, then small d is 1 millimeter, which is 10 power minus 3 meters, and capital D is 1 meter. So conversion is important. 500 nanometer should be converted, so you have to multiply it by 10 power minus 9. So 500 into 10 power minus 9 divided by small d is 10 power minus 3. Clear? So you will get beta. Now the second question is, here you can find the value. Okay, 500 into 10 power minus 9 by 10 power minus 3, that is 10 power minus 6, and here it is plus 2. So you will get 5 into 10 power minus 4 meters. Isn't it? Okay. Now the second part of this question is, listen, how many fringes can be seen in a space width of 10 power minus 2 meters? That is the question. That is, in this question you got the fringe width. Fringe width means is the separation, the distance between two consecutive bright or two consecutive dark. That is what called fringe width, isn't it? And it will be same, no? Even it is dark or bright, the value is same because all are having equal width. And here, how many fringes can be seen in a space width of 10 power minus 2 meters? How will you find that? If you are having the fringe width and the space width, how will you find the number of fringes? As number of fringes can be calculated by dividing the space width by what? Beta. Isn't it? As beta into number of fringes will give you the space width. That much space is covered. 10 power minus 2 meter is covered by this much fringes having a fringe width of 5 into 10 power minus 4 meter. That is the meaning, isn't it? So you can find the number of fringes like this. That is 10 power minus 2 divided by beta is 5 into 10 power minus 4. That is 5 into 10 squared. Clear? Or you can write it as 1 by 5 into 10 squared. This will come here. Isn't it? That is 100 by 5, which is 20 is the number. Clear? So number of fringes equal to space width by beta. Space width is given 10 power minus 2 and beta is also you find it from the previous question. It is 5 into 10 power minus 4. So after substitution you will get 1 by 5 into 10 squared, or 10 square is 100 by 5, which is 20. So how many fringes you can see there? As if the fringe width is 5 into 10 power minus 4 and the space width is 10 power minus 2, you will get 20 fringe. So let us move to the next question. A beam of light consisting of two wavelengths, 650 nanometer and 520 nanometer, is used to obtain interference fringes on a screen at a distance 1.2 meter from the slits of separation 2 mm in Young's double slit experiment. Find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometer. Okay, so here we have a beam of light. It consists of two wavelengths, and first is 650 nanometer and second is 520 nanometer. It is used to obtain the interference fringes on a screen at a distance 1.2 meter from the slits. So capital D is given. Then slits are separated by a distance of 2 millimeter. Small d is given. Lambda is there. Okay. You are asked to find the distance of the third bright fringe on the screen from the central maximum for the wavelength 650 nanometers. So first we are discussing the case for 650 nanometers. So in such a case you have to find the distance of the third bright fringe on the screen from the central maximum. Okay, you have capital D, small d, then lambda. Then what should be calculated is the distance x is to be calculated. Clear? So first we can write the given data, that is lambda equal to 650 nanometers, which is 650 into 10 raised to minus 9 meters. Then capital D is 1.2 meters. Okay, small d is 2 millimeter, which is 2 into 10 power minus 3 meters. This much clear. Now we have the number, that is third bright fringe, isn't it? So I can write n is given as 3 from the central. Clear? Now in terms of n and x, we have an expression for beta, that is x divided by n, isn't it? That is a space width divided by the number will give you beta. Okay. Also beta, we have expression d by d into lambda. Now you can equate these two, that is x by n is equal to d lambda by d. Or what is x? X equal to n d lambda by d. N d lambda by d. Clear? So now you can substitute, because x you have to find. That means in the screen from the central maximum to the third bright fringe, this distance you have to find. In between, first bright band is there, then second bright band is there, but each distance is same, right? So you can use this expression. Okay, this expression you have to keep in mind. And equating, what is the value? N is 3, capital D is 1.2, then lambda is 650 into 10 power minus 9 divided by small d is 2 into 10 power minus 3. Okay. Now you will get the value for x. So this is our first section of this question. Clear? Okay. Now the second part is, what is the least distance from the central maximum where the bright fringes due to both the wavelength coincide? What is the least distance from the central maximum where the bright fringes due to both the wavelength coincide? That is, we have two wavelength here, right? That is lambda 1 is given as 650 and lambda 2 is given as 520 nanometers, and at some distance, at some distance from the central maximum, in the question it is said that the bright band of lambda 1 coincides with the bright band of lambda 2. Okay, understood? That distance you have to find. Clear? That is from the central maximum at a particular value of x. That is a distance. At a particular value of x, the both wavelengths will coincide. Okay, wavelengths are given here. So you have to find that x by using the condition that the wavelength lambda 1 and wavelength lambda 2 coincides at that point. Okay, so let us move to that section. That is, suppose let us assume that let x be the least distance. From where? From the central maximum. From the central maximum where the bright fringes, first one I will take it as nth bright band, okay, nth bright band of the first wavelength, that is 650 nanometer, coincide with n plus 1 bright band of which wavelength? Second one, that is 520 nanometers. Okay, so this is just a condition to find that value, that is x is equal to, in the last value, no, the previous question you got one expression, that is x equal to n d lambda by d. Okay, n d lambda by d. So here also, how can you find? X is equal to, first condition is n into d lambda 1 by d. That is the first one. Okay. Now the second one is n plus 1 into d lambda 2 by d. Okay. This is also equal to what? X. That is the value that we have to find, least distance. So I can equate these two, that is n d lambda 1 by d is equal to n plus 1 d lambda 2 by d. Clear? So d and small d will get cancelled. Then how can I write? That is n lambda 1 is equal to n plus 1 into lambda 2. Okay. Now simplification is there. That is n lambda 1 equal to n lambda 2 plus lambda 2. That is n into lambda 1 minus lambda 2 is equal to lambda 2, or n equal to lambda 2 by lambda 1 minus lambda 2. Clear? Now substitute the values. You have lambda 2 and lambda 1. So when you are substituting there, lambda 2 is taken as 520 and lambda 1 minus lambda 2 will give you 650 minus 520, that is 130. 520 by 130 is 4. Okay. Now you can find the distance, that is x is equal to d n d lambda 1 by d, isn't it? That is, what is capital D here? Capital D is given as 1.2. Then lambda 1 is 650 into 10 raised to minus 9. N, now you got it as 4 divided by what is small d? As small d is 2 into 10 power minus 3. Clear? So you will get the answer in meters. Okay. So nice question. This is a textbook question. So go through it. First part is understand this equation. Okay, beta equal to x by n. How you got this equation? Then you can find the distance. The same thing here, second case we are applying. That is, we want to find the distance at which both the wavelength, the bright fringes due to both the wavelength coincide. So we are taking that condition here, and then you are equating and finding the value for x. Okay. with your given values you have to find it. It's a good question, go through it and practice more questions like this. Okay. So now before moving to the next question, let me introduce a topic, that is angular width, normally asking as conceptual questions in numerical section. So please listen here. This is your interference pattern. Okay, just a rough diagram. S1, S2 are the two sources, and this is how you are getting the interference pattern, equal intensity, equal width, etc. So this is your central maximum. You are getting a bright band. Okay, you can see that you are getting a bright band. Now this is your first dark. Okay, this is your first bright, again second dark, second bright, like that it goes. So these are bright and these are the dark points. Here also this is your dark point, again dark, this is bright, this is central bright. Okay, this is bright, like that this will go, and each and every point is of equal, each band is of equal width. Okay, now listen, you suppose I am considering these two dark bands. Okay, so this is the distance from the dark point to the central maximum. I will take it as x1, and this distance, that is the second dark to central maximum, I will take it as x2. Clear? Now what is this? Yes, this is x2. I can write x2 minus x1 is actually the fringe width beta, isn't it? x2 minus x1 is the fringe width beta. Now again here you can see this dark point is making an angle at this point with this central line. Clear? And again from this dark point also it is making an angle with the central line. Okay, now I can explain this like, suppose if this point, this dark point is making an angle of theta 1 and this is making an angle of theta 2 from this point. This is our second dark, this is first dark. Now this difference is called what? This difference is called the angular width. Clear? So angular width I can explain it as, if angular width is taken as theta, I can write it is the angle subtended. It is the angle subtended by adjacent bright or dark bands. Clear? At this point, suppose this is n, you can write at the point n. Okay, clear? Now listen, how can you find this? That is theta is equal to actually theta 2 minus theta 1, and here you are assuming that this theta is very small, so that you will go for tan theta. That is tan theta equal to tan theta 2 minus tan theta 1. Isn't it? Now this distance, you know, this is the distance from slits to screen, which we take it as capital D. Now listen, what is tan theta 1 here? Tan theta 1 is, you can see here, x1 by d, isn't it? So tan theta 1 is x1 by d and tan theta 2 is x2 by d. x2 by d. Clear? So x2 minus x1 by d, x2 minus x1 by d. And what is this x2 minus x1 is actually the fringe width beta, that is beta by d. Clear? Beta by d. So I can write this angular width in terms of beta. Angular width in terms of beta is theta is equal to beta by d. Okay, now beta, you have the expression d lambda by d, again divided by this d, which will give you lambda by d. So two expressions for angular width, they are theta is equal to beta by capital D or lambda by small d. Clear? Beta by capital D or lambda by small d. So keep it in mind and just understand how you got this. So this angular width is actually the angle subtended by adjacent bright or dark bands at the point here. Okay, now this can be calculated like this. Since the theta angle is very small, you can take the tan of the points. So finally you will get the expression like this. So angular width has two expressions, beta by capital D or lambda by small d. Okay, now we will move to our question. Listen to the question. In a YDSC using light of wavelength 600 nanometers, the angular width of a fringe formed on a distant screen is 0.1 degree. What is the spacing between two slits? Okay, so Young's double slit experiment, you are using a light of wavelength 600 nanometer. So lambda is 600 nanometers, that is 600 into 10 raised to minus 9 meters. Now the angular width is given, angular width theta is given, but it is in degree. 0.1 degree is given. You have to convert it into radian. You can convert it by multiplying with pi by 180. Pi by 180, that is you will get in radians. Clear? Now you want to find the spacing between two slits, that is D you have to find. Okay, so theta has two expressions as I told, beta by D as well as lambda by small d. So what is D? D is equal to lambda by theta. You can write that, isn't it? D is equal to lambda by theta. Okay, now substitute the values because you have lambda and theta here. That is D is equal to 600 into 10 raised to minus 9 divided by 0.1 into pi by 180. Now you get the answer in meters. That is your spacing between two slits. Clear? So just to understand this equation, I just explained the previous case. So now I think it is clear, because just be familiar with this equation, because numericals are always asked from this section regarding this angular width. Okay, so two equations, beta by d as well as lambda by d, according to the given data you can use the equation. So substitute and find the answer, calculate it and find. Okay, now we'll move to the next question. If two slits in YDSC have width ratio 1:4, find the ratio of intensity of maxima and minima in the interference pattern. So what about the question? If two slits in YDSC have width ratio 1:4. So width ratio is W1 by W2, which is 1/4. Find the ratio of intensity of maxima and minima. Intensity of maxima and minima you have to find. Okay, intensity of maxima and minima in the interference pattern. So you know the relationship between width of the slits, then intensity and amplitude. How? That is W1 by W2 is equal to I1 by I2, which is equal to A1 square by A2 square. This is your expression. This is a relation or connection between these width, intensity and amplitudes, isn't it? So you have, from this expression I can write A1 by A2 is equal to what? Root of W1 by W2, isn't it? Root of W1 by W2. So I have to find I maximum and I minimum. I maximum means what? I told this one, that is amplitude, sum of the amplitudes and then square. Again I minimum is difference of the amplitude and then squared, isn't it? So instead of A1 and A2, how can I write? Instead of A1 and A2 I can write root of W1 plus root of W2 divided by root of W1 minus root of W2 the whole squared. Clear? Clear? Now you can substitute the values. That is, you have the ratio 1 and 4. So root of W1 will be 1, isn't it? Root of W1 is 1 and root of W2 is 2. Okay, now substitute here. That is, you will get 1 plus 2 divided by 1 minus 2 the whole squared. That is 9, isn't it? 1 plus 2, that is 3 squared by minus 1 squared, that is plus 1, 9. So what is the ratio of the slates? Sorry, ratio of the intensity of maxima and minima? It is 9:1. 9:1. Clear? So I think today's class is clear for you. Go through the numericals, copy it to your notebook and practice more questions. Okay? If you have any doubt, contact me. Have a nice day and thank you.